2019 Nobel Prize in Physics is all about. He's extremely well qualified to do this. He did a bachelor's degree at Cornell. I only mentioned that because my son went there. So it's always good to say something about Cornell. But he did his graduate work at Princeton, received an MA and a PhD both in physics. And then he was a postdoc and a senior research associate at the University of Chicago for several years. And in 1983, he came to the University of Florida as an assistant professor, became a full professor by 1995, and in 2018 became professor emeritus. So he joined our ranks, several of us, and we're delighted to have him. I will say that he's been a visiting professor at Cambridge University, UC Santa Barbara, Fermi National Accelerator Lab, and the Institute of Astrophysics in Paris. And he's a fellow of the Astrophysics Division of the American Physical Society for contributions to the theory of large-scale cosmological structure, emphasizing nonlinear efforts and higher-order correlations. I think I'm going to leave that there. Let him explain that if he cares to. But today, his talk has to do with the Nobel Prize, which was awarded for contributions in 2019 to the understanding of the evolution of our universe and Earth's place, in the cosmos. Half of the prize went to James Peebles, the theoretical discoveries in physical cosmology, and half the prize was split between Michel Mayor and Didier Queloz for the discovery of an exoplanet orbiting a solar-type star. So, Jim, it's all yours. Welcome.
So, a year and a few months ago, October of 2019, I woke up the way I always do on the Tuesday of Nobel week. I typically wake up before 6 in the morning, and it's on NPR. And that year it wasn't on NPR, and I had to go poking around websites. And I discovered that the Nobel Prize in 2019 was awarded to my PhD supervisor. Jim Peebles is a Canadian, and they sometimes run to 4 names. So Philip James Edwin Peebles. And although the prize was split between cosmology and planets, I'm only prepared to talk about Jim Peebles because that's what I know about, and it's going to fill up a lot of time anyway. And the citation was for contributions to our understanding of the evolution of the universe and Earth's place in the cosmos, with a specific citation for theoretical discoveries in physical cosmology. Physical cosmology started in photograph. Of all the pictures that I saw on the web at the time, this is the one that looks most like the guy I know. This is his office. The lower row of books behind him is annual reviews in astronomy and astrophysics, and there are several dozen of them. And the shelf above looks like it's a bunch of people's bound PhD theses. He's got this cute smile. He's got a pin on his lapel, which I figured out later is the Order of Manitoba. Jim is Canadian. The the Nobel Prize people do these caricatures, and this this caricature of Jim doesn't quite look like the way I envision him. In particular, the chin looks too narrow, but if you look around the web, you can find exactly the photograph that the artist used. And so you can see that there's a narrow center to his chin, and then it fills out around. And then CNN and a bunch of other people. And there's even a photo from his high school graduation with honors in science even then. So the story goes back to 1965. Before this event, cosmology was sort of metaphysics and theology and perfect cosmological principle and a lot of what ifs. But two guys at Bell Labs playing with a new radio receiver found something that they couldn't account for, and eventually figured out that they were looking at a remnant from the early history of the universe. Bell Labs, Crawford Hill is not far from Princeton, and they, from Bell Labs and the Princeton people, started talking to each other, and they published two papers back to back in the Astrophysical Journal. Penzias and Wilson was a short piece that just said excess antenna temperature at some number of gigahertz. And then the Penzias and Wilson paper said a possible explanation is in this accompanying paper. And the accompanying paper by Bob Dickey and Jim Peebles and Peter Roll and David Wilkinson talks about what a hot Big Bang would have been like. Although there are four authors on the paper, Jim is the one who did most of the theory work that led to this figure. And this one figure, published on the first day of physical cosmology, sort of has everything that we do now. The history of the universe from today, which is the far right on the graph, back to a temperature of billions of degrees. And the universe expands, going from left to right. It cools off, going from left to right. The temperature, which is one of these lines, slants down. The density of the cosmic background radiation is another one of these lines sloping down. And the density of matter has a more complicated history, and it's another one of these lines sloping down. At early times, the universe is a complete plasma. Everything is relativistic. It's opaque to everything, even neutrinos, which now pass through a whole universe without interacting with anything. Eventually, it reaches a point where it says helium formation is possible. And this universe that's just a plasma turns into hydrogen and helium and a little bit of other stuff. A little bit later on, it says transition from radiation to matter.
Message for you, son.
Excuse me, that's my email. And a little after that, it says transition from radiation to, it says plasma recombines. That's the second vertical line. And almost everything that's part of the Big Bang model today is part of this figure. Peter Roll and David Wilkinson were actively looking for the microwave background radiation. when Penzias and Wilson stumbled on it. They did publish their discovery just the next winter. Bob Dickey was sort of the grand old man in charge of the group, and Jim Peebles was the young theorist. Penzias and Wilson won the Nobel Prize for discovering the microwave background. That was awarded in 1978. And so we'll talk more about that later. Meanwhile, all of these aspects of the behavior of a physical universe, Jim studied in more detail over the next 10 or 15 years. And so here are a bunch of, it's amusing to me that at the end of this paper on the history of the universe, it says this research was supported in part by the National Science Foundation, which is good, but also by the Office of Naval Research. The Navy used to support blue skies scientific research until somebody in the decades following this decided that the Navy would only support things that had direct applications to weapon systems. Primordial helium abundance. The universe, when it's about a temperature of 1 billion degrees, turns into about 1/4 helium. And about a part in 100,000 of deuterium. And nobody's found any other way to make substantial amounts of deuterium except in a cooling hot Big Bang. And this is one of the observations that underpins the hot Big Bang. So that was a year later. Another year after that, the recombination of the primeval plasma. At early times, the universe is full of hydrogen and it's hot, and so hydrogen is ionized, and photons scatter off of charged particles, and the universe is opaque, you can't see through it. But when it cools off through about the ionization energy of hydrogen, the hydrogen nucleus and the electron recombine to become neutral, and the neutral hydrogen atom doesn't interact with radiation very much, and the radiation from that point onwards free streams to the detectors that we see as the cosmic microwave background radiation. Jim and Bob Dickey started talking about the formation of structure. Gravity likes to bind things together, and their calculations indicated that the earliest things to form should be the globular star clusters that we see a bunch of orbiting the Milky Way. Galaxies rotate, and so here's a piece about the origin of the angular momentum of galaxies. When the radiation and matter decouple, when the plasma recombines, there are patterns of things imprinted on both. And Jim Peebles and JRU figured out how that works. And Jim and Jerry Oestreicher in a neighboring building on the Princeton University campus figured out that without dark matter, spiral galaxies wouldn't be flat disks, but bigger puffy things. And Jim figured out that without dark matter, there wouldn't be any fluctuations to grow up to become galaxies. And this is the beginning of dark matter. And Bharat Ratra, who was a postdoc at Princeton, came to talk to Jim about the dynamics of a scalar field coupled to gravitation. And so they talked about cosmological constant and a time variable cosmological constant. And this is the beginnings of dark energy. So here's a summary of all of these things. the observation of the microwave background, computation of the helium abundance, recombination, globular clusters, rotating galaxies, coupling of matter to radiation, dark matter in the structure of galaxies, dark matter in the fluctuations that grow up to be galaxies, and adding dark energy to the whole thing. What's that? That's over a period of about 2 decades. And that basically is the model of the universe that we still believe in today. Sean Carroll, who posts on Twitter, says it is not an exaggeration to say that modern cosmology consists largely of a series of footnotes to Jim Peebles. So there have been Nobel Prizes awarded for a lot of this. Penzias and Wilson were the first to see the microwave background radiation at all. John Mather and George Smoot, representing the Kobe satellite, received Nobel Prize in 2006 for demonstrating that the radiation is precisely black body. That was the FIRAS spectrometer on the Kobe satellite. And George Smoot for measuring small anisotropies, differences in the temperature in different directions that are related to the origins of galaxies. So the calculations that underlie that are Jim's recombination and Peebles and U, adiabatic perturbations, plus some of the dark matter stuff, plus some of the dark energy stuff. And a time variable cosmological constant leads to an acceleration of the expansion of the universe. And Saul Perlmutter, Brian Schmidt and Adam Rees received a Nobel Prize in 2011 for measurements of large redshift supernovae that established that this effect was part of our universe. And although Jim was underneath all of this, we sort of felt that either he'd missed the moment or the right moment had never come. It certainly would not be possible to give a Nobel Prize to Wilkinson and Roll without giving it to Penzias and Wilson. And the Nobel Prize rules are that you can't give it to more than, well, it's 3 people in physics. And Penzias and Wilson were certainly first. And Mather and Smoot did the satellite observations, and Perlmutter, Schmidt, and Rees did the supernova observations. And the other problem is that the Nobel Prize is sort of supposed to be given for a specific benchmark results. And this is all of everything, but it's too diffuse. So in 2019, the Nobel Prize Committee broke these rules. Jim is the first theorist to win a Nobel Prize for cosmology, the universe. And the award seems to be for a life's work. It's for all of this instead of just this or just this or just this. Certainly the first paper lays it all out. Bob Dickey and Dave Wilkinson are no longer with us, and Peter Roll went off in a different direction. So maybe it's for the first one. Then talk about what Jim did after some of this earlier stuff. And this involves pictures. This involves what was going on when I was in graduate school at Princeton. Of all the pictures that you see of the universe, of the distribution of stuff in the universe, this is one of my favorite. This is a picture of the distribution on the sky of galaxies brighter than 19th magnitude. And I don't even know what that means exactly, except astronomers measure brightness in magnitudes, and the bigger the number, the fainter they are. And in 1967, 19 was pretty faint. Now they go out to 27. So this represents a distance which is about 1% of the size of the universe. And this is just looking at sort of the night sky spread out above you, except that you're seeing galaxies instead of stars. And it's a representation of observations made by Don Shane and Carl Wertman. It's not individual galaxies, but it's the brightness is proportional to the number of galaxies in little boxes on the sky. So where it's white, there are many. Where it's black, there are few. And this represents the sky overhead spread out over maybe 2/3 of the sky. The center is the North Galactic Pole, and the corners are maybe 50, 60 degrees away from the North Galactic Pole. So it's a fair fraction of the sky. And if you look at this, you can see two aspects of matter in the universe. First of all, if you just sort of blur your eyes, the picture is just a textured gray, and the gray level is pretty much the same from one side of the picture to the other. And the fact that it's sort of the same from one side to the other is the statement that the universe on large scales is homogeneous and isotropic, pretty much the same one place as another, pretty much the same one direction as another. But if you focus your eyes, you see that there are bright spots and dark splotches. There's a bright splotch right in the center of the picture, which is the Coma cluster of galaxies. The Coma cluster is as close to the North Galactic Pole as Polaris is to the Earth's North Pole. And every bright spot that your eye picks out is a cluster of galaxies that's in somebody's catalog or another. At maybe 2 o'clock and maybe halfway out is another bright spot, which is the cluster Abell 1367, the 1367th cluster in a catalog of clusters made by George Abell. And they're bigger splotches. In the bottom left is what's called the Serpens Virgo cloud. And so the distribution of galaxies is random in a sense, but it's not uniformly random. It is clustered. And the nature of those clusters, Jim Peebles likes to say, are the equivalent of our fossilized dinosaur footprints. They tell us about things that were happening earlier in the universe. This catalog was made at Lick Observatory. I'll go back to that later. Lick Observatory sits on Mount Hamilton above San Jose, south of San Francisco. If you are driving down Interstate 280? I forget the number. If you're driving from San Francisco to San Jose on the interstate, you can see this observatory on the top. Unfortunately, last fall, there was a fire that came very, very close to the university, to the observatory. But the fire crews managed to preserve the historical structure, the data they represent. The historic Carnegie Double Astrograph Telescope was used to take those data. Here is a picture, not from that telescope, but a picture of a cluster of galaxies. And galaxies are what we look at. So the big blotches that you see are mostly spiral galaxies or elliptical galaxies, but there are smaller ones that are all galaxies. But actually, every dot of light that you can see in this picture is a galaxy. And Shane and Wortman spent a couple of decades of their life counting galaxies brighter than 19th magnitude as seen from Lick Observatory. They started taking photographs of the night sky after World War II, from about 1947 to about 1958. And they take a photographic plate, they put a grid on it, and they count galaxies in a grid. Von Shane and Carl Wertman each did this, and they did it by hand. So here is one of thousands of pages from a data book. And this 0022030222 is counting by eye under a microscope the number of galaxies, so these little splotches that they could see in a square grid put on top of a photographic plate. In the 1950s and the 1960s, there are 36 by 36 of these numbers for each page. There are 1,246 photographic plates and 1,296 numbers on each plate. And that's 1 million pieces of data. It's a couple million pieces of data. And there was no way to publish that. So they did counts in 6 degree by 6 degree boxes. So the darker boxes on here. And they published that in the Astronomical Journal. And eventually the entire thing was published in Publications of Lick Observatory, which was the complete 1967. And there was no way at that time to make use of this. But by 10 years later, by the mid-70s, computers had gotten better. Jim Peebles had gotten interesting in the statistics of galaxies. So another of his papers, the theory of galaxy count statistics. When I entered graduate school in the fall of 1974, Jim was giving a special topics course on the large-scale structure of the universe, and he handed out mimeographed lecture notes. So here is an attempt to copy one of the pages. Mimeographed text fades with time. The light sort of gets into the edges more than it does in the center. So at the top it says, nature of the large-scale distribution of matter, I think. And this was the 0th draft of what became his second book. We worked with computer data people to turn all these numbers into digital bits and did studies of them. For a decade, Jim Peebles had a Sid Harris cartoon on his door, which is the astronomer sitting at the back of the telescope. It had a caption on the bottom that said, "Stop thinking about all those galaxies." And in the mid-70s, Jim and Ed Groth studied the two-point correlation function of galaxies. What that means, and the answer is in this plot, is that you are more likely to find a galaxy near a galaxy than you are in a random place. The density of galaxies in the neighborhood of a galaxy rises more and more as you get closer and closer. And Jim and Ed did the two-point function and the three-point function. And when I went to ask Jim about working with him, before he said he didn't feel comfortable inflicting another unemployed cosmologist on the world. I said I didn't care if I ended up driving a taxi in New York City. This stuff was so interesting, I wanted to work on it. He said, well, we did the two and the three-point function, and so maybe you can work on the four-point function. And he just started doodling on a piece of paper. And I still have that piece of paper. So I did the four-point function of galaxies, which shows that four galaxies like to be near each other more than just random or random pairs or random triples. And this is a demonstration that the distribution of matter is sort of wheels within wheels within wheels, what Jim calls a continuous clustering hierarchy. And this, again, is the basis of the whole subject today. And people go out and do this with surveys that look the whole distance to the edge of the galaxy instead of just 3% to the edge of the galaxy. And Jim, here's a photo of Don Shane, who was one of the authors of the survey. And he's not wearing his glasses in the picture, but he had very thick glasses from looking at galaxies under a microscope for decades. And three of Jim's graduate students, Ray Sanira and Mike Seldner and myself, Jim, in his Nobel talk, said, somehow graduate students seem to show up when you need people to work on things.
Which one is you?
I am second from the left. Does my mouse not show up on the share screen? Anyway, Don Shane, and then me, and then Ray Sanira, and then Mike Seldner, who both ended up at Bell Labs. Jim has a number of books published. The first one was called Physical Cosmology. And it's an elaboration of all of the ideas in his first decade of papers. And one called The Large Scale Version of all of the ideas in his second decade.
Dr. Fry, you're frozen. Hold on a minute.
I got...
Dr. Fry, can you hear me? Dr. Fry?
I'm here, but...
Okay. We might have missed a little bit of what you were saying. You froze for a minute.
We good? Are we back? Okay.
Give it a go. Okay, go ahead.
I pulled a picture off the Princeton University Press website. 2 days after the Nobel Prize, and they'd already stuck this little logo, winner of the Nobel Prize in Physics, on the book cover. In the 90s, he did the principles of physical cosmology with another distribution of galaxies in color. And in the first decade of 2000, Jim Peebles, along with 2 Princeton colleagues, did Finding the Big Bang. And this is a still from a video of Jim talking about what's in the book, presented at the Institut d'Astrophysique de Paris. And you can find the video, I think it's on YouTube, and if it's not, it's on the IAP website. And so you can track it down. And then Jim has another book that's just new last spring, Cosmology Century, an inside history of our modern understanding of the universe. When Jim was announced as the Nobel Prize winner, I sent him an email in which I said, in part, now you can become a philosopher. And he said he felt more comfortable being an historian. So this is a history of the subject. All of his books are highly technical, but this might be the most readable if you want to give it a go. And then some of the reaction. The Nobel Prize is problematic for some people. There are now, only 2 women to have won the Physics Nobel Prize. People always complain when it's yet another elderly white male. All of the people complain, say, Jim is the nicest guy, and he should have it if anybody does. Neil Turok said, normally I would congratulate somebody for winning the Nobel Prize, and of course I do, but today I congratulate the Nobel Prize on awarding it to Jim Peebles. Jim, over a bunch of different interviews, said things that I've excerpted. My life has been quiet and suddenly it's not. My life will go on. I was about to say unchanged. Maybe that can't be true, but I'll try not to let it change me much. People ask him, how did you know to do this? And he just said, I could think of 1 or 2 things to do and just did them and kept going. And then he talks about the development of physical cosmology from nothing to a precision science. Over the years, the uncertainties in the things measured have gone from a factor of 2 or 3 to 10% to 1% to tenths of percents. And it still works. The way he envisioned it in 1965 is still true. Jim is Canadian, and they interviewed him in his hometown newspaper. And he said, there are 2 things you can do in science. One is to work on sure things. It's maybe dull, but it's guaranteed to lead to incremental progress. Or there are speculative things that you don't know what will happen at all, but it can be exciting. He said both. Are we frozen again? So he likes the speculative part. Feeling uneasy, but it turned out to work. And now the evidence for the hot Big Bang is so tight that it's established there is a Big Bang, Virginia. And finally, I can't see this, no way. Over the decades, you can imagine that Jim Peebles not winning the Nobel Prize earlier has had to answer many times, how do you feel about not winning the Nobel Prize? And he was always very generous. It's true that there are many people who have not won the Nobel Prize who deserved it. I'll name Victor Weisskopf just for one. Prizes come or they don't. Don't worry about it. Do it because you enjoy doing it. Judge yourself by how well you have done and do your best. Okay, so that's the end of my PDF.
Thank you. John or Ken, you want to make any comments?
No, I have some questions, but I'd rather let the participants ask them. And if they don't, I'll ask them.
John Axe, do you have anything?
I think that I really appreciated that talk. As a non-physicist, I think I got the gist of the talk without any problem. And we passed over all of those numbers and large equations that you didn't mention that were on the slides. So I'm grateful for that. Thank you, Jim.
I said we didn't mention any of the equations, and there were only a few that were visible, and they were there as art.
Well, let me ask about a couple of things. One is that in that first diagram, you had a timeline that started, it was in seconds, 10 to the 4th, 10 to the 8th, 10 to the 12th seconds. And I was trying to figure out quickly on my calculator, what is 10 to the 12th seconds? And you know, it's and I didn't quite finish that, but we're talking, everything took place just within a few minutes and hours, most of the stuff.
Do you want me to put this back up on the screen?
Yeah, just for a second. Look at that. That time scale is really interesting.
So, where is share screen? And I find the screen and share. Is it there?
Yeah, there it is at the top. Units of seconds. So we're talking, by the time you got helium formation, it's 10 to the 4th seconds, which is
yes, I could have said that.
An hour or so.
Well, so helium is before 10 to the 4 seconds. And so an hour is 3,600 seconds. So 10 to the 4 is about an hour. But the start of the formation of helium is in fact 3 minutes. And that is Steven Weinberg's book, The First 3 Minutes.
I see, yeah.
10 to the 8 is about 3 years.
Mm-hmm.
And 10 to the 12 is then, so
30,000 years. Yeah.
30 million seconds is a year. And the end is 10 billion years.
Oh, yeah.
13 billion years.
That's where we are.
That's where we are.
Yeah. Good. Also, I had a question about the photograph of all the galaxies is a two-dimensional thing.
Yes.
And do you estimate the three-dimensionality of it by the redshift or by certain stars within those galaxies, or? In other words, yeah, that picture with a few dozen or a few hundred in color, the next one.
So this is two-dimensional. This
Right.
is, we say, projected onto the sphere of the sky.
Right.
These days, we do have studies with distance information, typically from redshift, although there are ways to measure distance independent of redshift.
Mm.
So the information that you get from them has more details, but the one is related to the other by summing over the line of sight. This is well, a projection of the other. And it's the same, whenever you look at a photograph, you see a two-dimensional representation of what's out there.
Yeah.
And whenever you take a photo of, the mountains, it never looks the same in the photo that it does when you are actually viewing it by eye, because you're adding a lot of distance cues and you have more information than is in the photograph.
Right.
But you can still infer all the information you need about the universe from doing it. It's just integrating out the line of sight.
Right. Right.
Yeah.
Are there any limitations to the size of the universe that we have any idea about?
Oh, we can only see, my water's gone too. We can only see what we call the horizon, which is basically the universe is 13 billion years old and we can see 13 billion light years. We can't see any further than that. The universe becomes opaque. So the part that we can see is a little bit less than the 13 billion light years because you reach a wall. And people speculate about what might be out there and are there any observational implications? And so not yet.
Yeah, because I mean, the obvious question is if there actually is a limitation or a size, what's on the other side? What else is up there?
Somebody says, please explain the Planck epoch. So I don't really know how to explain the Planck epoch, except the universe, as it gets larger, cools off. So if you run it backwards, it's hotter. And it gets hotter and hotter, and it reaches atomic physics temperature, and then it reaches nuclear physics temperature, and then it reaches particle physics temperature. And eventually it becomes so hot and dense that it reaches a scale called the Planck energy, which is where quantum gravity takes over. And we don't know what happens in quantum gravity. And so that's another reason we don't know what happened before, because we don't have the rules in order to do the calculation. But this question of what happened before the Big Bang, or there's another question, how many universes are there? There's the multiverse these days. So somewhere out there, maybe there's another universe exactly like ours. I was at a conference at the University of Chicago that was endowed by the Pritzkers, the people who own
Chicago.
Marriott. And So we all stayed at the Marriott and took buses to the University of Chicago campus. And there was an NPR reporter on the bus. And the day after we talked about the multiverse in the sessions, he went down the rows asking people how many universes they thought there were. And the person in front of me said there were as many universes as there were cosmologists. And I had about a minute to prepare an answer to this question. So when he got to me, I said that one universe was enough to keep me busy. And so the part of the universe we know about is enough to keep us busy. And we'll make incremental extensions backwards, maybe, but somebody else, not me.
I think John Axe has a question.
Yes, thank you for a very nice talk. It seems to be that the Nobel Prize Committee is catching up on people just before they die because you cannot give posthumous Nobel Prizes. There was John Goodenough, who was, got one for lithium batteries when he was in his 90s. And then there was this guy from Bell Laboratories, whose name I forgot, who worked on laser tweezers, who was in his late 90s and still working in his basement on laser tweezers. I think Jim Peebles' time has come, and I'm very glad that he finally got a recommendation. But I want to tell you a little story, which I think John Reiskin has already heard. I worked at Bell Laboratories, and there was a man named Ray Davis who spent his career looking for neutrino oscillation, looking for solar neutrinos. And I got a letter one day from the Nobel Prize Committee asking me if I had any people that I would recommend for the Nobel Prize. I had played tennis with Ray Davis. And so I thought, well, maybe I'll try to get Ray Davis. So I went to the head of the laboratory. I went to the head of the chemistry department. I was in the physics department. And together we put together a letter of recommendation for Ray Davis for his work on solar neutrinos. We never heard anything back. But 20 years later, he got the Nobel Prize. He was in his late 80s. He had had a stroke and he was unable to speak. He sat in the audience while his son gave the Nobel Prize talk. He's also a physicist at the University of Chicago. In that case, the problem was Ray Davis had the correct number for his experiment. That was the number of the kind of neutrinos that he was looking for that come from the sun. What he did not know, and what finally happened that earned him a part of a Nobel Prize, was that another group of people using different kind of detectors found that neutrinos change from one to the other on their way to the Earth. And so Ray Davis's work was perfect, but I'm sure that our recommendation for him was turned down because he was obviously having answers that were not predicted by the theory at the time. So I just think that's an interesting comment on the way Nobel Prizes are given out.
And he was right, and it's too bad he had to wait for the theorists to catch up.
Yeah. It was sad. I was watching him sitting there while the Nobel Prize was given, and I felt very sad.
Ron Drever missed out on the Nobel Prize for gravitational waves by just a little bit. Somebody points out that the Planck epoch is the first 10 to the minus 44 seconds, which is true as a number, if that tells you any more than you knew before.
Right.
Okay, I don't see any other questions. Any final comments? Oh, Izzy, I'm
Once
sorry.
again, I'd like to thank Jim very much.
I'm sorry, Ken. I see Izzy's hand.
Oh, is he?
You get to thank Dr. Fry again, but Izzy, go ahead.
This is way out question, but at the University of Florida, are they still doing radio astronomy, particularly at Jupiter?
Well, Tommy Carr is no longer doing it. So they don't do radio astronomy in this department. They do infrared astronomy.
Tom was one of my professors, but he's no longer with us.
No.
Yeah. Well, I taught a course with him on extraterrestrial civilizations. Let me ask you one last question about Peebles. Was he a good graduate advisor? Did he read your dissertation? And
he was perfect for me. He let me just do my own thing, and once a month report on progress and make a few comments and suggestions. That's not the best. Some people need daily guidance.
Right.
But he's also one of the nicest guys that I've ever met. Well,
that's good.
I could talk for hours.
Nice guys should get Nobels.
Every now and then.
Every now and then, yeah.
Thank you.
I had a lab between two guys who won the Nobel Prize in '78, and that prize was really appreciated because these are two of the world's most unassuming individuals. So people were really thrilled that a couple like that would actually win. Anyway, once again, thank you, Jim. Look forward to seeing you next semester.
Save up your questions and ask them then. Thank you all. See you again.
Thank you so much.